discussion based on a topic dimensionality reduction technique. Since this is a part of a group activity which is followed in SLS institutions, my students are here to present you a group discussion which is based on this topic. Let us see how my students are going to do the process efficiently. Thank you.
Good morning to one and all present here. Now we are going to discuss a topic about dimensionality reduction techniques. And the participants are myself, Sri Michael, Umar, Madan Kumar and Naveen. Dimensionality reduction is an essential technique used in data science, especially when working with high dimensional data. It helps with visualization, feature selection and even improving model performance by reducing noise and redundancy. Let's start with the classical approaches. Umar, can you explain PCA and LDA?
Sure, PCA, Principal Component Analysis, is one of the most widely used technique. It's work by finding the direction of maximum variance is high dimensional data and projecting it onto a smaller set of principal components. This helping future extraction and reducing redundancy, but PCA is unsupervised, meaning it does not consider class level.
That makes sense. Since PCA just looks at variance, does it always work well for classification?
Not always. Since PCA only consider variance, it may not always separate different classes effectively. That's where LDA, linear discriminant analysis. Since PCA only consider variance, it may not always separate different classes effectively. That where LDA, linear discriminant analysis, comes in. Unlike PCA, LDA is a supervised method that maximizes classes separability by finding a lower dimensional space where intra-class variance is minimized and inter-class variance is maximized. This makes LDA more suitable for classification tasks.
So, in simple terms, PCA is best when just to compress the data and remove the redundancy, while LDA is better in classification in our goal, right?
Exactly. PCA is used in exploratory data analysis and pre-processing variance. LDA is mainly used for supervised classification.
Great points. But PCA and LDA are both linear methods. Naveen, can you explain how non-linear techniques like manifold learning addresses their limitations?
Yes, absolutely. Linear assume that the data points are flows, where I always manifold learning techniques are non-linear in data by high dimensional point, icon and lower dimensional fields. Some popular manifold learning techniques are t-SNE, UMAP, uniform manifold approximation projection, isomap, used for geostatic distance to maintain the original high demand distance.
That's interesting. So, can these methods be used for feature selection?
Not exactly. Unlike PCA and LDA, manifold learning methods provide explicit selection features. They are mainly used for dimensionality reduction, making features important ranking.
I see. So while PCA and the LDA give a transformed feature space that we can use in machine learning model, t-SNE and UMAP are better on exploratory data analysis.
Yes, that's a good way to put it.
Interesting. Another area related to dimensionality reduction in matrix learning. How does that fit in?
Great question. Metric learning is different because instead of reducing the dimension explicitly, it learns the distance function to better a group similar to data points. For example, in face recognition, instead of reducing the feature dimension directly, the metric learning ensures the image of the same person are close in embedding space while different faces are far apart. This is commonly done using contrastive loss, triplet loss, or Sesame's network.
So, metric learning is more about improving similarity measures rather than explicitly reducing dimensions.
Exactly. It is widely used in recommendation system, image retrieval, and clustering.
Naveen, we talked about classical and manifold learning techniques. How do deep learning methods like autoencoders help in dimensionality reduction?
Autoencoders are a type of neural network designed specifically for underserved specialized learning. They are encoder and decoder. Encoder compress the input into lower dimensionality reduction code. Decoder reconstruct the original input from this compressed input. Unlike PCA, which linear and autocoder can learn complex and non-linear relationships, making useful for images, speech, and embedding.
That's fascinating. How do encoders compare with PCA?
PCA is purely linear, meaning might capture complex patterns of the data. And autoencoder, on the other hand, can model non-linear structure, making them more flexible. However, they can require data and computational power.
That makes sense. But are autoencoder just used for compression?
Not necessarily. Autoencoder can also use it for decoding data, anomaly detection, and future extraction. A good example is validation autoencoder (VAE), which helpful to generate same from learned distributions.
This discussion has covered a lot of grounds. To wrap up, let's discuss when we have used each technique in real-world applications.
For structured numerical dataset like finance or sensor data, PCA or LDA would be ideal due to their simplicity and interpretability.
Similarly, for high-dimensional data, nonlinear data like images and word embeddings, I would go with the manifold learning or metric learning, depending on the problem.
If you have resources, deep learning based autoencoder are the best capturing complex patterns and learn about the future extraction.
So the best techniques depends on the dataset and the problem at hand. If interpretability and efficiency are key, PC and LDA are great. If we need better visualization, manifold learning works, and for deep learning applications, autoencoders and metric learning shine. Thanks everyone. This discussion gave us a deeper understanding of different dimensional detection techniques and their trade-offs. It's clear that no single method fits all problems, and choosing the right approach depends on the data, computational constraint at the end of goal. Thank you.